In this video, I want to talk about Nastran coordinate systems, orientation vectors, offsets, and deflections. Now, I really did not rehearse this, so I apologize if the video is a little rough around the edges, but I think this video might help a few new Nastran users understand what's going on when it comes to coordinate systems, orientation vectors, offsets, and deflections. So now, let me jump here and start talking. Okay, Nastran gives you three types of coordinate systems. You have a rectangular coordinate system, a cylindrical coordinate system, and then you have a spherical coordinate system. If you look in the quick reference guide, let me go ahead and close some of these windows. Let me go all the way to the beginning, chord to S maybe. Here what I want to do is look at this expression. Each of these coordinate systems have their own special behaviors that I want to point out. The rectangular coordinate systems are pretty straightforward, so maybe we can just glance at that. So the rectangular coordinate system, let me briefly talk about that. Rectangular, cylindrical, and spherical coordinate system. Let's talk about vectors in each of these coordinate systems. Okay, so suppose we have a point here, GA, and this is our rectangular coordinate system that we've defined. I'll call it CID 5. If we want to define a vector, it's pretty simple. A vector here in this coordinate system is simply this. You walk along, and here let's say we want to look at 1, 1, 0. What does that vector look like? We walk along the x, we walk along the y, and we walk along the z. So here, this is our vector at GA in this coordinate system. What does the vector look like in the cylindrical coordinate system? This is where it gets a little complicated. Suppose we have this coordinate system here, r, theta, and z. Let's suppose we have some point here. And how do we get to that point? So we start at some radius, maybe 5, a radius of 5, and we rotate maybe 45 degrees. So this point is at this position, 5, 45 degrees, 0. Now, what does the vector 1, 1, 1 look like at this point? So let me explain what that vector looks like. So there is a unit vector from the origin to that point that I will call r hat. There's another vector, theta hat, and there's another vector that is in this direction, which is parallel to this axis at the bottom right, that I will call z hat. To keep it simple, I won't include that element axis for now. So here, how do I get theta hat? When you start here, some distance r, and then you rotate, this vector theta hat is tangent to this rotation. So that's how I got r hat. Now, once you get r hat, theta hat, and z hat, r hat is now the x component of displacement. Theta hat is the y component, and z hat is the z component. So what does this mean? This is what the vector 1, 1, 1 looks like. You walk along the x, you walk along the y, and then you walk along the z, which is kind of out of plane. So this is now my vector 1, 1, 1 in the cylindrical coordinate system for this point. And this is going to be very important when you're dealing with orientation vectors, deflections, and cylindrical coordinate systems, and so on and so on. So now, let me repeat this process for the same point somewhere else. So let's go ahead and suppose that we have this point, which could be at 590 degrees and 0. So what we're doing is we're going out some radius and then we're rotating. Remember that theta hat is tangent to the rotation. And then r hat is going to be from that point to the origin of the cylindrical coordinate system. And so this is going to be our x, this is going to be our y. So what does that vector look like? So we walk along the x by 1, we walk along the y by 1, and then we walk out of plane by 1, so the vector will look something like this. So when you define a point in a cylindrical coordinate system, when you define the point, it's a radius, theta, and then a z. Whenever you define a vector, though, this is defined in rectangular coordinates in this, I don't know what to call it, maybe the unit vector coordinate system. And you'll see that depending on where the point is, each different point is going to create its own unit vector system, if you will. It's in this unit vector system where you define the vectors. So here, for the vector 1, 1, 1, this vector at this point looks like this. The same vector, but at a different point, looks like this. And the same is true for a spherical coordinate system. Let's go ahead and maybe delete some of this. Let's go ahead and delete this, this, and that. And let me just leave this example. So let's see, how does that coordinate system look like? So this is going to be the R. Actually, let me look at that. So it's going to be the R. Let me look at this for a moment. So here we'll draw it like this. This is another coordinate system that maybe we'll call CID 7. This is the radius, this is the theta, and this is the phi. So you could think of this as the before the x, the y, and the z, if you really want to look at it from that perspective. Okay, so what's going on here? This one gets a little confusing, so I think it might be worth looking at this diagram while I am working on this. So here, let's do a point. So maybe, okay, so whenever you start with this coordinate system, you start at the origin. You start with the first component. So let's suppose we want to plot 1, 45, and 90. What is that going to look like? So we start here, we walk along the phi axis, and then we rotate theta, and then we rotate about the phi axis. So here, let's go ahead and do this. So we already know one thing. This is the r hat. This right here is going to be the theta hat. Am I doing that? I think it's phi hat, actually. No, that's theta. Right, okay. So that's going to be theta hat, and then your phi, maybe we'll leave phi 0 for now, just so we don't get too confused. Or actually, I need to include it, actually. Okay, so once you're here, you'll need to rotate this by phi. So this is going to be your theta hat, and then this right here is going to be your phi hat. Actually, what I'm going to do, and this is what happens when you do it on the first try. Instead of that example, let me just use the example they have in the documentation. So here they have this. And the point they have looks like it's about here, point P. So what do you do first? This looks like it's let me add some depth here. Let's suppose it's here, P. And now what's going on? So you could think this was your R axis, your theta axis, I believe, and then your phi axis. What is this point in spherical coordinates? So maybe it's some distance 1, and then it's been rotated maybe 45 degrees. And then maybe it's been rotated, I don't know, 30 degrees as an example. So let's look at this. First, you walk some distance along the phi axis. So here, since r equals 1, you walk a distance r equals 1. And then you rotate by some theta. So here, theta is 45 degrees. And then you rotate by phi degrees. So what is that going to look like? So you can think that this is theta hat because it's tangent to this theta rotation. And then here, this phi rotation, this is going to give you a tangent vector, phi hat. And then r, the r hat, that's always from the origin to the point. So it's going to look something like this, r hat. So this is what the unit vectors look like at that point. I know it's very complicated, but we have to have this discussion if we're going to have success with spherical coordinates. So once you have this, this becomes your x-axis. So this is 145 and 30. This becomes your x-axis, this becomes your y-axis, and this becomes your z-axis. So what does the vector 1, 1 look like? So here we're going to walk along the x, we're going to walk along the y, and we're going to walk along the z-axis. So then here, from here to here, this is our vector. I'm running out of room here, so I'll draw it here. This is our vector 1, 1, 0. So wherever you are, let's go ahead and suppose we have a different point. Here, the unit vectors are actually different. The unit vectors might look something like this. This is r hat. And then my phi, let's go ahead and assume phi is in this direction. I could be wrong. And then my theta is going to be here. So here, if we walk along the x, we walk along the y, and then the z, this vector, which we defined as 1, 1, 1, depending on where the point is in the spherical or the cylindrical coordinate system, the vectors could be in completely different directions. So now, let's talk about orientation vectors. So what is an orientation vector? So let's suppose you have some point GA, some GB. You're dealing with maybe a C bar, a C bush, a C beam, and it's asking you to define an orientation vector. So how is the orientation vector used? So number one, you draw a line from GA to GB. Typically, this defines the positive x element axis. So here you could think that x element is from GA to GB. And then you have this orientation vector which has been defined. After this, you need to find z element and y element. So how do you find these other axes? Z element is equal to the following. It's the cross product between x element and the orientation vector. And once you have z element, you can find the element axis for y, which is going to be, okay, let me look at this. Z element crossed with x element. So once you define GA, GB, you know what x element acts, you know what this vector is. After this, you need to specify the orientation vector v here. Once you have these two pieces of information, you can use the cross product to determine what your z element axis is. So let's go ahead and do this. Let's suppose that this is my x, this is my y, and then this is my z. Oh, wrong direction. So this is my z. And now I define an orientation that is maybe like this. So we're going to walk along the x, walk along the y, but then I'm going to walk backwards in the z. So then maybe this vector is negative, positive 1, negative 1. And let me look at this. Or actually, should I use that? Yeah, that's going to work. Maybe, yeah, that's going to work. So this is my orientation vector. So you do the cross products, you get a normal. This is going to be your z element axis. You do the normal or the cross product between z element and x element, and so then you get the y element axis. And then at this point, we could just ignore the orientation vector. And you'll notice that when you take the cross products like this, we get orthogonal vectors, and this defines the element coordinate system orientation, at least for your C bar, your C bush, and your C beam. So that is the orientation vector. What else do I want to look at? Offsets and deflections, right? So let's go ahead and do this. So let's talk about offsets. So this is a vector. An offset is also a vector. When do you use an offset? Suppose you have GA and GB, and we want to create a beam. Oh, this is not a good beam. Draw it again. Suppose you want to define a beam like this. You need to orient, or if you need to orient, we just had a discussion on that. But one thing you can define are what are called offsets. So let's go ahead and do this. Let's suppose that this is here at the top right, this is x and this is y for the basic coordinate system, which has an ID of 0, and an out of plane would be z. Let's suppose that you want to offset the shear center as an example. So the shear center might be offset like this. Suppose you want to offset it by -1 and then +1. So the offset would have this vector, a -1, +1, 0. And we'll use the same vector for the other end. So -1, +1, and 0. And these vectors are defined in the displacement coordinate system for GA and GB. I'll talk more about the displacement coordinate system in a moment. So offsets are defined in the displacement coordinate system CS. So here, this is the profile, you will, of the shear center. So then once we orient our beam, this is what our offset beam might look like. And here, let me draw it again. Sometimes I like getting a good beam that has good perspective. So here it might look like this. So it might look something like that. So this is GAGB, maybe the C bar as an example. When you apply the offset, this dotted line is now your shear center. By default, the offsets are 0. So the shear center is aligned with the line element of the C-bar element. So remember, this offset is a vector. So if you're dealing with a cylindrical coordinate system as an example, so here let's go ahead and draw one. Let's use cylindrical r theta. Suppose that we have a beam element that looks like this. And we want to offset the shear center as an example. Maybe we want to offset the shear center. So it's here, then this is the cross section, not the cross section, but this is looking at the beam from the top, if you will. So what do we do here? So like before, we determined those unit vectors. So we have r, we rotate. So this is r theta, or r hat rather. This is theta hat. And then z hat is coming out of the plane. We do the same thing for this other point. So this is my r theta, r hat rather, and then theta hat. And let me separate this a little bit more. So now these are my unit vectors here in the cylindrical coordinate system. And remember, GA, GB have been set to use, or rather, GA and GB's displacement coordinate system have been configured to use this displacement coordinate system. So that's why we have to find this r hat, theta hat for both ends, GA and GB. Now, once we have those unit vectors, we have an idea of what my x, my y directions are. So if I want to offset this beam shear center, what would the offset be? The offset would be maybe a 5, 0, 0, close. So here, r hat is the x. So we're going to walk here. So this is my vector 5, 0, 0. And then here we're going to use the same vector 5, 0, 0. So that's how you use an offset in a cylindrical coordinate system. I'm going to skip the spherical coordinate system because that one gets really complicated really quickly. So I'm going to skip that for today. So that's an offset. Now the last thing I want to leave you off with are displacement coordinate systems. Think of a displacement coordinate system like this. Suppose you have 2 points. So here we've defined one coordinate system here. We'll use a rectangular coordinate system. CID equals 1. Here we'll use a cylindrical coordinate system. So R, theta, and then Z. We'll call this CID 2. Every point can be thought of having a different observer, if you will, a displacement coordinate system, if you will. For the rectangular coordinate system, the observing displacement coordinate system, the axes are parallel to the original coordinate system. So here, this is X, and this is Y, and this is Z at this point. For this point also, X, Y, and Z. And personally, what I like to do is I like to draw a stick figure here, and I like to draw a stick figure here. We have observer 1 and observer 2. Here, since it's rectangular, both of these observers are kind of agreeing with one another if you kind of think about it. But as you've seen in a cylindrical or spherical coordinate system, it's slightly more complicated. Here, this is my r hat, theta hat, and then z hat is out of plane. And then the same thing here. This is r hat, theta hat, and then z hat is coming out of plane. This is my x, this is my y, this is my y, and this is my x here. So what happens here? I want to draw an observer. So here I'm going to draw a stick figure. I'm going to do that here too. And why does this matter? When you look at a Nastran analysis, these displacements are reported in the displacement coordinate system. So here, let's suppose that this displacement coordinate system is cylindrical. For these two, the displacement coordinate system is this rectangular coordinate system. Let's suppose that the observers, let's suppose both deflections for now are 1, 0, 0 for both. And here it's really simple. That means that this point has walked here by 1 unit. So this is our new point. Here, this observer too, it's seen that the point has moved by 1 unit. So this is our new location of the points. What happens if those are the same deflections in the cylindrical coordinate system? Let's suppose that when we looked here, the displacements was 1, 0, 0. What is that going to look like here? So a displacement of 1, 0, 0, 0 or 1, 0, 0 is going to look like this. You're going to walk along the x by 1, and so this is the new point. So you have a radial direction, if you will. Here, you're going to walk from this point, you're going to walk along the x by 1 also. So this is your new location for the 2 points. Now, let me do another few comments. Let me look at this. So this is going to be if the vector was defined in the displacement coordinate system. Right. So here, let me go ahead and create a new page, and let me do a few last comments. So when you work with the grid entry, there are 2 coordinate systems you can use on that entry. Grid ID rather. So grid, okay, here, reference and analysis coordinate system. Okay, so let's talk about the grid entry. So grid, here, let me do this. So grid looks like this, an ID, a CP, X1, X2, X3, and then CD. I'll skip fields 8 and 9 for now. Let's talk about this entry right now. So when you look at the grid entry, you can supply the coordinate system in 2 places, the CP field and the CD field. The CP field is the reference coordinate system, if you will. You could think of it like this. I'll say that this is the CP coordinate system. So there's X, Y, and the Z. And we'll call that maybe CID1 for now. So think of this as like a construction coordinate system. There's one observer here at this coordinate system. This coordinate system is going to dictate the position of the grid. So as an example, let's suppose we want to put a point here in this coordinate system. So with respect to this observer or this coordinate system, that point is going to be situated maybe at 1, comma 1, comma 0, 1, comma 1, comma 0. So let's go ahead and draw that entry. Grid ID, we'll call it 101 for now, and then the CID is 1, and then the location is going to be 1, comma 1, comma 0. But then you have another coordinate system that maybe is a cylindrical coordinate system. So here you're saying, you know what? Yeah, I use this coordinate system to position the grid, but during the analysis, when I look at the displacements, I want to view them in this coordinate system. So then you go through that procedure of drawing your r hat, your theta hat. So your theta r hat. So this is going to be your x and your y. And then you have to position your observer. Here I like to use the y-axis as the up direction for my observer. So here in the CD field, here if this cylindrical coordinate system had ID 5, here I will specify that CD is 5 here. So then what happens when you look at the displacements? So here, the position has units of length because the reference coordinate system is a rectangular coordinate system, so it has units of length. The displacement coordinate system, when we look at the results, they will also be in units of length, but they will be in this displacement coordinate system that you see here. So here, this observer is going to be looking at the displacements in this orientation. If we had a different point, maybe here, maybe this point is 1, 45 degrees, 0, this orientation would be slightly different. R hat would look something like this. Theta hat might look something like this. So my orientation, my observer will look something like this. Okay, now let's see what else is there to do. Let's talk about the reference, which is the CP field, and the displacement coordinate system, CS, which is the CD field. Let me make sure I have these fields correct. Right. Let's talk about units. Okay, so if you're dealing with rectangular coordinate systems, the units are length. So you have X, Y, Z. Those are in units of length. Cylindrical. The units are different. So you have an R, a theta, and a Z. So here you have length. You have degrees. And then you have length again. So this could be a meter, an inch, and so on and so on. Spherical. And let me look at the notes on spherical real quick. And here I'm just flipping through some O notes I've done earlier today. Theta and phi. So this will have units of length. Degrees, I'll use the degree symbol, and degrees again. Now when you look at your final results, this is what you're going to get. For translations, they're going to be XYZ, 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 and all of these are going to be in length units. And remember, for a rectangular coordinate system, the process is a little simple. But when you're dealing with spherical, cylindrical coordinate systems, the orientation of the observer is going to change. Now, what about rotations? What are the units of that? So you're going to get an Rx, Ry, and Rz. Rx, Ry, and Rz. Rx, Ry, and Rz. So these are the rotations. All of these are going to be in radians. So I know these notes are a little hard to understand. I think what I recommend is as you follow along, take your own notes so it's a little bit more legible on your end. Unfortunately, the tablet I'm using, it's very glossy. Its coefficient of friction is basically really, really low. So I'm basically writing on butter. So that's why some of the letters might be not legible on your end. And let me have one last comment here. So let's look at one example here. Let's look at a few examples here. And maybe I'll call this C. And let me just do 2 points for now. Let me do 1 point actually. So let's take a look at this entry. So that entry, if you look at the CP field, it's blank. So when it's blank, it's defaulting to CID 0, which is the basic coordinate system. It's technically not the global coordinate system, but if it's your first day using Nastran, think of it as a global coordinate system. So where is this point? So we walk along so this is the origin here at the bottom. So we walk along the X, we walk along the Y. So this is our point, 1, 1, 0. So this is our construction. This is our reference coordinate system. So here we drew an observer that's telling me, okay, from my perspective, this point is located here. And now, what if we wanted to change the displacement coordinate system? So right now, the CD field is blank. So when the CD field is blank, that means it's defaulting to CID 0, which is again the element or the basic coordinate system. So the coordinate system at this point is going to look like this: X, Y, then outer plane is Z. So here I always like to draw my observer here. So here, when you look at your deflections, they're going to be in this coordinate system that you see here. But suppose I wanted to use some other coordinate system. Here in this example, maybe I created a cylindrical coordinate system with ID 5. So let's go ahead and draw this coordinate system here. And then outer plane would be Z. How do I say, you know what? I don't want to observe my displacements using this observer. I want to use a different observer. I want to use a cylindrical coordinate system. So how do we do that? So let's recap. So my R hat looks like this. My R or theta hat looks like this. So this would be my X, my Y, and then my Z. Well, that would be in this case it'd be in this direction, Z hat. So this would be the Z. So then I have a new observer here. I'll draw his head, draw his legs, and his arms. So then, what do I do to this grid entry to get this new observer? I type in 5 here. And then I save, I run the analysis, and when I look at the results, these results would be in that coordinate system, that displacement coordinate system. Now, if today is your first day using Nastran, then that field, which is field 7, it's most likely blank or set to 0. If it's blank or set to 0, you're using the basic coordinate system to look at your displacement. So let me draw that just so you see what the observation or observer looks like. So this would be my X, this would be my Y, and this would be my Z. So here in this case, CP is blank. So the default is used, so CID 0. CD is also blank. CID is 0. So here if I draw multiple points, all of these points, as long as you use blanks for all of these points, they're all going to share displacement coordinate systems with parallel axes, if you will. So let me give you an example. So here, 2, 3, and 4. Here I've defined various points. So all of these points are going to have these displacement coordinate systems, if you will. But if I switch to the cylindrical coordinate system, that's when you're going to have a lot of fun. So here, let me quickly draw what those look like. So this is theta hat, r theta. This is a theta hat, or r hat, theta hat. And this is going to be r hat, theta hat. And then Z is going to come out of the plane. So you can think that each one is going to have its own observer. I think you get the point. So here's where I use, I'm using CP blank. So the default is 0. And CD has now been set to 5. So when you have CD equals 5, these deflections, if you will, these are going to be observed in these different unit vector coordinate systems, if you will. Okay, then let's see. So we went over Nastran coordinate systems. We went over the units. We went over a reference coordinate system for grids. We did the same for displacement. Sometimes you'll hear this referred to as the analysis coordinate system. We went over vectors. This is very important because for cylindrical or spherical coordinate systems, the same vector, here I'll just use this example, the same vector will have different orientations. The vectors are very important if we're working with orientation vectors for C-beam, C-bush, C-bar. If you're defining offsets for the shear center in a C-beam, you will use that there. And deflections. A deflection is also a vector. So this was a very quick overview of Nastran coordinate systems. I did not rehearse this, but I wanted this information to get out there because I know some new users are going to struggle trying to understand all of this. For myself, I also struggled. And for me, what's really helping me at this point is thinking in this regard. Whenever you think about a grid and it's moving, ask yourself, what's the coordinate system that the results are being observed in? Is it a rectangular coordinate system? Is it a cylindrical or spherical coordinate system? So this is for a grid. And the same is true for a beam element. So let me go ahead and... So when you have a beam element, is the same thing. You're going to have the X would be in this direction, X element. Maybe your Y is like this, and then your Z element looks something like this. So here, again, there would be an observer. And when you look at your shear forces or your moments, you're observing these beam results from this observer. What's in there? Another example, quadrilateral elements also. There is an element coordinate system here. So when you're looking at the stress, there is an observer here, if you will. And why is it important for a 2D element? Let's suppose you have these two elements. So two triangular elements. Maybe your element coordinate system might look like this for this first element, but then the element coordinate system for the other element might look like this. When you look at the F06 file, you're going to get a theta, let's say we're looking at the stresses, sigma x, sigma y, and sigma z. Those results are going to be in the element coordinate system. So when you're looking at maybe, you look at one stress is maybe positive 100, and the adjacent element is negative 100, and you might ask, okay, why? To me, all the stresses should be going in the y direction. But in the F06, I'm getting different signs even though the elements are right next to each other. This is because you're looking at the results from this observer for each element. So for me, when I was learning Nastran, coordinate systems, so on and so on, I always think of that stick figure. What does the observer's position and orientation look like? Am I looking at the results at a grid? Is the grid in a cylindrical coordinate system? Is it in spherical? If I'm looking at beam results, what does that observer look like? If I'm looking at the results of 2D elements like a C quad or a C tria 3 or 6, what do the observers look like there? So like I said, this wasn't rehearsed. I've been wanting to make this video for the longest time, and I decided, you know what, planning it would just take me a whole day, so I decided to just get on my computer and make this video. Let me leave you off with one last comment. Remember, this observer could possibly help you. It helped me, and that's the last thing I wanted to leave you off with. Thank you for watching.